Bonjour à toutes et tous et merci d'être là pour assister à ce séminaire. As the presentation of Miguel is going to be in English, so let's switch quickly to English. And please let me first present and welcome to Professor Miguel Anjos. And Miguel actually is, he holds the chair of operation research at the School of Mathematics at the University of Edinburgh. And actually his research interests are in the theory, algorithms, and applications of mathematical optimization. He has had research collaborations with plenty of partner industries. Some of them we know them very well, so such as India, for example, but also Expretio, Hydro-Quebec, National Grid, ESO, etc., and so on. He's the founding academic director of the Trotter Institute for Energy at Polytechnic of Montreal. And he's actually president of the Informs section in Energy, Natural Resources, and the Environment, and Informs vice president for international activities. He's an author of more than 100, let's say, interesting research papers. So the presentation of today will be with a more focus on semi-definite optimization approaches for reactive optimal power flow problems. So thanks a lot, Miguel, for have accepted the presentation of SystemX to this seminar of SystemX, and the floor is yours.
Thank you. Thank you very much, Maclouf. Merci beaucoup. Ça me fait plaisir d'être ici. Merci à tous ceux qui sont là, en ligne ou en personne. Je vais faire ma présentation en anglais, mais je répondrai avec plaisir à des questions en français. Donc, n'hésitez pas. The presentation that I'm giving today is on, as Maclouf said, semi-definite optimization, and it has to do with applying it to what are called reactive optimal power flow problems. And these are problems that come from operating high voltage networks. And so this work was done in collaboration with both RTE in France and Hydro-Quebec in Quebec, as part of the industrial chair that supported the work. So what I'm going to do today is an overview of several projects that were done within this umbrella, and with some technical details in parts to give you a sense of how semi-definite optimization comes into this. And there's also a whole list of co-authors, so colleagues from Polytechnique Montreal. Thank you. So very quick outline. I'm going to basically give you a bit of motivation and background and the contributions of this whole piece of work, talk about semi-definite approaches to AC optimal power flow, and then discuss different ways of trying to solve these problems. So I'm going to talk about something called clique merging per coil relaxations very briefly, really for lack of time, and then talk about how to integrate practical constraints for reactive optimal power flow, and talk about a branch and bound algorithm to come up with global solutions for the problem, summarizing everything at the end. What we're talking about, or what I'm talking about today, is optimal power flow. And the basic idea is to say we have a AC power network, and we want to find what's called an operating point. So we have a certain amount of generation, a certain amount of demand, and we want to find, when the network is stable, how is the power going to flow from generation to demand? That is what we want to optimize. What we can change in terms of the inputs is traditionally one would change the generation, so the demand would be fixed, and we would want to change the generation to meet the demand at minimum cost. For example, with thermal generators, when you start introducing renewables, when you start introducing other things, the objective may change. In the work with Hydro-Quebec in particular, because there's a lot of hydro generation, we think about minimizing the losses. So in some sense, generation is not really, the cost of generation is not really the issue. What we want to do is minimize losses. So there's different ways that one can think about the problem, but that we want to optimize some objective and find the best operating point for the network. This is in general a difficult problem for alternating current, in particular because we have non-convex power flow constraints. And this is known to be a very hard problem. It was first written down in the way that we still look at it today back in 1962 by Carpentier. And in 2015, there was a theorem that shows that even just testing feasibility is strongly NP-hard. So we're trying to solve a problem for which we don't even necessarily know in advance there is a solution. And even just checking if there is a solution is a very hard problem in general. So it's not quite as bad as it sounds, but it is definitely a very difficult problem. One of the challenges is also that there are a lot of local optima. So when you optimize a nonlinear optimization problem, you tend to find solutions that are locally optimal, minima or maxima, but there's no guarantee that it is the best solution overall. And for this problem, it is particularly difficult to do that as well. So what there is from a practical perspective, people who run networks and want to solve these problems is a significant lack of solution techniques that are both fast and robust. If you want to be robust, you have to work very hard at it. If you want to be fast, you're not necessarily confident of what you're getting. And it's trying to get the two together that is the big challenge. In fact, it's a significant enough challenge that in the United States, there's a challenge going on funded by the Department of Energy that says the ultimate objective is that we want to have software to find global optimal solutions up to 3 to 5 orders of magnitude faster than existing solvers. So it's not just 3 times faster, it's 3 times orders of magnitude faster. It's a major speed up because real world networks are very, very large. And there was a quantification in a DOE report that said that if we could do this in the US alone, this would mean saving $10 billion annually. And this got people very excited, and in particular got something called the grid optimization competition going that started back in 2000. Well, the idea goes back a while, but the first challenge started in 2018, 2019. Just go back.
Et avec le sourire.
Pour venir en arrière.
Oh, okay.
C'est bon. So this is done in multiple challenges. There was challenge 1 that finished in February 2020, challenge 2 that brings in some themes related to optimal power flow, second part of challenge 2, challenge 3 is starting. So this is really done in stages to work towards this ultimate big tool that can do everything very fast. And at each stage, there's significant amounts of money in terms of prizes. The only catch is you have to be based in the US to get a prize. So that's the only thing. Otherwise, anyone can participate. So there is serious interest in solving these kinds of problems. The version that I'm talking about today is what's usually called the reactive optimal power flow, which means that we want to compute this optimal power flow, as I mentioned before, but we have not only the non-convex power flow constraints to deal with, but we also have decisions that are discrete. So in particular, we're going to assume that we have devices called shunts on the system that can be turned on or off. And whether they're on or off will change the behavior of the system at that point, and in general. And then we also have transformers that have multiple settings in terms of tap ratios, and we can optimize that. But again, these are discrete. They're specific values that they have to be at. So we're taking a nonlinear hard problem and adding integer variables to it. That's really what this means. So this is generally even harder than the basic ACOPF. So what this collaboration with the various people that I mentioned has done is resulted in the following distribution. So the first thing, as I said, we're considering semi-definite optimization. So we considered an improved algorithm for solving semi-definite optimization relaxations, and I'll speak a little bit about this. Then we design new semi-definite relaxations for the reactive OPF problem that in particular improve significantly and allow us to solve problems with more than 3,000 buses. Bus here is a node in graph theory language. We also introduce some practical aspects coming from the interest from industry, wrap the whole thing into a branch and bound approach, and in the end, we're able to get optimal or near optimal solutions for problems with up to 10,000 buses, which is quite exciting in this context. And finally, perhaps the most exciting piece from the practical perspective is that we can actually find feasible solutions that are better than those from rounding heuristics in the literature that are often used just because the problem is so hard. So we also have quality guarantees coming in. This is a slide just to give you a sense of what the mathematics look like. This is the basic ACOPF formulation. So we want to minimize, in this case, output generation cost. So C is the unit generation cost, P is the amount of real power generated. We have power balance equations that say that at each bus or at each node in the network, power in equals power out. And we have line flow equations that model the flow of power on each line. And there is a flow in one direction and there is another flow in the other direction. So there's two flows per line. Everything is in complex, here everything things are in complex numbers. Up here also the voltages are complex. These are real equations, one for the real power, one for the reactive power. These are the real and complex parts of the power as a variable. So we're really optimizing over complex numbers is what it boils down to. And then we have linear bounds on some of these quantities to keep things under control. Typically, the voltage angles shouldn't vary too much because you want to stay close to the operating values for the phase angles of the voltages. And we fix one of the buses, the angle to 0, because these are relative quantities. So the constraints down here are fairly simple and straightforward. The action is really between the power balance equations and the linear flow equations that are nonlinear quadratic equations, quadratic non-convex equations in complex numbers. Now, what has been done in terms of attacking this problem, broadly speaking, there's three different categories of techniques. One of them is to say, well, this is a nonlinear optimization problem, use a nonlinear optimization solver. The main drawback is that you get a local optimum and there's no easy way of determining how good it is and whether there might be better solutions elsewhere. However, if you do have a good starting point, if you know where you're looking, where you want to look, then this works very well. So that is the advantage, is that the nonlinear solvers work very well, but you have to know where you want to look. And this relates to what I'll talk about a bit later. A second approach is to linearize, and typically you would turn the AC power flow into a direct current or something similar to direct current to linearize things. And then you have a linear optimization problem. And then the third approach is to look at not linear, but still convex relaxations of the non-convex constraints. And this is the point, the direction that this work is in. There's been a significant amount of work already done in this area. There's looking at these basic DC approximations, looking at what are called spatial branch and bound algorithms, which unfortunately I don't have time to get into. Some of the work done here in Paris by people on the plateau. Looking at Lasserre hierarchy for the relaxations, work done at EDF. And then there's really lots of papers looking at even just specifically the semi-definite approach. And there was a survey in 2020 that does a very good overview of what had been done until about 3 years ago or so. So there's already quite a bit of work in this direction. And what is the fundamental idea? The fundamental idea is to look at the ACOPF, so this optimization problem I showed you before, and say, okay, we have a quadratic non-convex problem on complex variables. You can look at this as a polynomial optimization problem in complex variables. So the fact that it's quadratic it happens to be the degree that you have. We have some general polynomial, and there is a way to linearize polynomials using semi-definite programming that is well known, that in fact connects to the Lasserre relaxations that I mentioned in the previous slide. There is a really useful observation, which is that in fact, if you focus in, the nonlinearities only involves the voltage. Okay, if I back up 2 slides, if you look, for example, at the first equation, everything is linear except the term in the voltage with the VK squared. So we have a complex number squared. Same thing in the second one. Here, it's a little bit less obvious, but the blue quantities are constants. So here, it's really V times V and V times VK times VK, VK times VM. So again, it's quadratic in voltages. So it's not quite as bad as it seems when we start looking at it. And so let's focus on the voltages. And the idea is to use a matrix variable to linearize the squares of the voltages. So we define a matrix variable capital V for voltage, where we have on the diagonal of that matrix variables the voltage squared, the norm of the voltage squared, and the off diagonal is the product of 2 voltage terms in the appropriate complex way. Now, if you do this, this matrix has some interesting properties. In particular, you can take a set of voltages and you can create this matrix, but the question is, if you have a set of numbers in the matrix, can you get voltages back? And it turns out that you can do this under certain conditions, and that's why, in general, we have a relaxation and not necessarily an exact solution. And there is the question of how do you extract a solution from having solved the relaxation. If we forget about that for a moment, using this technique, we can basically linearize the quadratic terms of the OPF. This is very messy to do. It's not hard, but it's messy. And in particular, Julie Slivak, as part of her PhD, developed a Julia module that just does it for you. So in general, if you take a polynomial problem in complex formulation, this will do the processing to give you the linearization and avoid a lot of hard work and mistakes along the way. Oops, I went more than one. Yeah. So what happens here if we do this for the equations that I showed you? Well, the V squareds become the terms in red, VKK. In the line flow equations, again, I take the appropriate products of voltages and linearize. So these are now linear in the matrix V. All the constraints at the bottom here are also linear in V. The only thing that's left is this matrix definition constraint at the very bottom. And this is where the difficulty is now. I basically made everything else easier, but given myself this extra piece that I have to handle. And this is where all the non-convexity difficulty is hiding. And if we could solve this with equal at the bottom, then we have an exact formulation. What we do is we do a semi-definite relaxation. So we use the fact that the condition that we want, V equals to little v Hermitian, holds if and only if the matrix V is positive semi-definite and the rank is 1. What we do is we drop the rank and we just use the positive semi-definite condition. So we have a necessary but not sufficient condition to have a solution. If it turns out that we solve this computationally and we find a rank 1 solution, then we actually have solved the problem to global optimality. And sometimes this happens. And if it happens, then we actually have a guarantee that we have 0 optimality gap and we've solved the global optimization problem. Now, this was done for various kinds of combinatorial optimization problems and other kinds of problems before it was done for OPF. It was done for the first time for OPF in 2008 in a paper by Bai and co-authors. What got people in ACOPF very excited is that a paper by Lava and Low in 2012 actually used this for IEEE benchmarks at the time and showed that they got the global optimal solution for all, which got a lot of attention. They also did more than that in terms of the theory, but the fact that suddenly this seemed to be solving what were considered difficult benchmark problems got people very, very interested. It didn't take very long to realize that this was not true in general, and in particular for some practical cases, this failed, but it still looked promising. It still looked very good. Even when you try to make it look bad, it's hard to make it look bad in some sense. So there was a lot of interest and excitement in this approach. What is still a limitation is the fact that this is computationally very expensive when you go for a bigger problem. So this is much more expensive than linear optimization, for example. But you get really quality out of the solutions in general. So what can be done? This is a one slide on the chordal relaxation approach for semi-definite programming. This is a very general technique. It's not just for ACOPF. I will not get into the details because it takes me a whole talk just to go through all the details. And I'm not exaggerating. It is really interesting, subtle mathematical theory. What I want to do is just give you the idea of how this works. This is an approach that was proposed about a bit more than 20 years ago to exploit sparsity in semi-definite optimization in general. And basically the idea is to say we have a positive semi-definite constraint on a large matrix. We're going to decompose it into a bunch of smaller matrices. So we have V positive semi-definite, and we want to write something like, this is true if and only if a whole bunch of conditions on a whole bunch of different matrices Xi is positive semi-definite. And we can have a lot of these matrices Xi, but we want them to be much, much smaller than our big matrix. So think of this as breaking up the problem into a whole bunch of small, much smaller matrices, which is cheaper computationally, but there's no free lunch. You need to have the smaller matrices, but you're also going to have constraints linking the entries between these matrices. There has to be connections between them. They're not completely disconnected. So you break your big matrix into a bunch of small ones, but then you have to have constraints that link them appropriately. Okay. There is a way of doing this that is, there's multiple ways of doing this. In fact, there's many different ways of doing this. The ones that we want to focus on are the ones where the resulting graph, where the graph representing the sparsity pattern of this matrix V is chordal. Chordal basically means the following. You take your matrix V, you put a node for each row and column, and you put an edge between two nodes if the entry row column has a non-zero element. Remember, we're talking about sparsity here. So there's going to be a lot of zeros. We ignore the zeros. We want to look at the non-zeros in this big matrix V. And then we want to make sure that if we do the sparsity pattern of the matrix V, it has the property of chordal, which means that any cycle of 4 or more nodes has at least one chord in it. You don't have big open cycles. Okay, you only have triangles essentially. And so this is the condition that you need to make this work if and only if in these two directions. Okay, otherwise you don't have a guarantee for the if and only if. This is well understood. People know how this all works. If you have a pattern of V that is chordal, this then motivates the idea of using chordality for ACOPF. And this was done within the last 10 years. And one of the contributions in Spivak's thesis was an improved algorithm for doing this structuring of the chordality. The real trade-off here that is still an open question, this is the last thing I'm going to mention on chordality, is the trade-off between the size of the matrices and the number of constraints. Roughly speaking, the smaller you make the matrices, the more conditions you need to link them. And computationally, both hurt. Meaning, if the matrices are big, this hurts. If you have a lot of constraints linking them, this hurts. So you have to find the right balance between what is your block decomposition and what are your linking constraints. And this is really the open question. Even for ACOPF, but even in general, not only for ACOPF, but even in general for STP, how do you trade off these two things? And so if you want to know more about this, there's a really exciting open question hiding behind these lines that nobody knows how to do in general. Now, getting back to ACOPF and now bringing in the reactive part, as I mentioned, what we're going to do is bring in shunts and tap changers and looking at definite relaxations for that. What does that mean in practice? It means that we revisit these constraints from the ACOPF, so the power balance constraints at the buses, and we introduce a variable U here at each bus K where there is a shunt. And this is a binary variable because the shunt is either on or off. So now we have a quadratic term times a binary variable. And in the other equations, in the line balance equations, when we bring in tap changes or transformers, these T's that were in blue before, because they were constants, are now variables. And they are integer variables. And typically there's some range of tap values that, depending on your transformer, there's a certain number of values that this can take. So now we have degree 3 polynomial constraints with binary variables at the top. And we have expressions with variables at the top and the bottom in terms of fractions and degree 2 or more. What do? We basically apply the same ideas from the semi-definite approach before. We linearize the voltages using a matrix V. We take the ratios V over T, we give them a new name. This is always the trick in optimization. If you've got something you don't like, give it a new name, makes it look better. And now we embed these new names, these W's, which are V's over T's, into some larger matrices as before to represent the products of V's and T's, which are the terms that we need to linearize. So I'll skip the details, but this is basically what you need to linearize the expressions I showed you. And then we have the X's, which are the new names for binary times linearized voltage. So first we linearize the voltage, then we linearize binary times the voltage. And we end up with everything being linearized, but of course, all these new variables, you need to link them with appropriate constraints. You relax everything to semi-definite in terms of the matrices, and then you try to put appropriate bounds on these things. One of the interesting ideas is to say, let me back up one moment. Here I have these 3x3 matrices for the terms V over T. And I have the large matrix V. So before I was talking about breaking V into blocks. One thing I can do is take sub-blocks of V that look like the 3x3 matrix here. So in particular, I can say for each line in the system, I'm going to have a 3x3 coming out of the big matrix. And instead of having the if and only if that I was talking about before, you just go one way. You relax it further. You just say, forget the big matrix. I'm just going to have a bunch of 3x3 blocks. So it makes things easier. And this gives what we call the tight and cheap relaxation, because it does exactly what the name says. We have a bunch of 3x3 blocks only, and a few more constraints to tighten things up a bit. And then we can extend that idea to the case where we have the tap changers. What we do here is we look at these ratios and we say, okay, what do we do with these expressions that we have? We have V over T and V over T squared. And this is part of the thesis of Christian Benganet, where he considers a 4-dimensional set that represents the kinds of expressions that we're looking at. And he derives an exact formulation for the convex hull, which is the best you can do in terms of relaxing and linearizing the set. You pull it all together. So this is the proposition for the exact convex hull. You pull it all together, you get some extra constraints for the relaxations. And now you've got a bunch of relaxations that you can solve, whether you do the full relaxation or the tight and cheap, and whether you use the convex hull or not. And you get fractional solutions. You can round the fractional solutions to integer. And the nice thing is that if you round and you match the value of your relaxation, then you know you have a global optimal solution. And if you don't, you know how far you are potentially from the global optimal solution. And now kicks in this trick that I mentioned before. We've solved the relaxation. We get some values for the integer variables. We fix those. And now we can say we have a nonlinear problem. We can just use a nonlinear solver. And we can use the continuous part of the STP solution as a starting point. And this works really, really well. This is not my idea. Other people have thought of it before me, but definitely it works extremely well to do this, this approach. So in summary, if we look at the combination of all these techniques, we end up with what we call tight and cheap relaxation number 2 that gives the best combination and is certainly very competitive even for very large problems. I think I've got, yeah, just a very quick mention that if we focus on shunts, in practice, you cannot just turn everything on and off all the time. There's a dynamic to how the system works. So the way I set up the problem, it says you can put the settings you want to optimize. In practice, you might say, well, there's only so many that you can switch on in one time period. Or you have a current state and you can only make so many changes going to the next state. So we put some extra constraints on the shunts to reflect that. Or we also can say, well, you're going to have a solution, but then depending on what needs to be done for adjusting the frequency, we might have to move the generators up or down. And then what we want to do is to do it in a fair way. So this is defined here that if we have to go up, everybody goes up in proportion to the amount of generation that they're doing. And if you're going down, same thing, which means that everybody hits 0 at the same time if we have to go all the way down to 0. So it's trying to impose fairness. It gets a bit confusing on the mathematics, but that's really what this expression means. I'll skip this piece for the sake of time. What you can now do is integrate all this into the semi-definite definition of relaxation approach and get a branch and bound. So now this is the slide with a whole bunch of technical details for the branch and bound. How am I doing for time? Probably.
I think we still have 15 minutes.
15 minutes, yeah. Okay. So I can just very quickly give you an idea of these settings. What we do in the branch and bound, and we solve the semi-definite relaxation at each node using MOSEC. There's a question of which one to use. You can use any one you want at this point. We use the clique decomposition algorithm approach to speed things up. We use, when we want to use a nonlinear solver, we use, we get feasible solutions using Nitro, which is a nonlinear optimization solver, and we use what's called the MPEG option. This is a very nice idea, which is to say we express the binary variables as complementarities. So a variable is 0 or 1 if the variable times 1 minus the variable is equal to 0. And this turns out to be what's called a complementarity constraint. Nitro has a special way of handling that, and it guarantees you a binary solution coming out of solving it. So this is a very useful trick. We branch on the binary variables only, so technically we're not actually doing a full branch and bound, and we don't achieve necessarily global optimality because of the continuous parts of the problem. So this is also important to keep in mind. We do a depth first search. We branch on the variable closest to 1. So we don't branch on the most fractional. We branch on the least fractional. The reason being, we want to aim for feasibility. Oftentimes, even just finding a feasible solution is hard. So we run the branch and bound focusing on feasibility. We give a time limit of an hour for these results reported here. we also cut corners a bit in that when we see at a node variables that are sufficiently close to 0, sufficiently close to 1, we fix them. Again, to speed things up towards feasibility. So there's a strong focus on feasibility and global bounds in this approach. Depending on the kinds of constraints that we put on the shunts, we get somewhat different results, but the basic idea is that there's a bunch of test cases here going from 300 buses to 13,659. I'll point out that these ones that end with RTE are versions of the French network in different configurations. So there's about half a dozen of them that are used in research nowadays. If you just solve the root node with the semi-definite relaxation that we used here and don't do any branching, in some cases we get a 0% gap. Those are the blue ones in the root gap column. So that means you're done. You've got a rank 1 matrix, you've got a full solution, you've got integers, everything is wonderful. If that doesn't work, then we have to go into the branch and bound to the right, to the columns on the right. And then in some cases, again, the blues reflect the cases where the branch and bound close the gap to 0, the dark blues, within 1 hour of computation. The light blues are the ones where the branch and bound improved the bound but didn't get to 0. There's one at 0.44 in this case. And the red ones are the ones where the branch and bound made no difference. So you put in all this extra work and you haven't really gotten any further than the root node. So that tends to happen for the bigger problems down here, where you really just run out of time, essentially. But in many cases, you do improve. And then the last column is the rounding gap. So this is an approach from the literature that takes the outcome of the semi-definite relaxation at the root and rounds the solution to get the best possible solution in that approach. So in these cases, the rounding works fairly well, but the key point here, until the line, but the key point here is that if you look at the big instances, the rounding generally doesn't work at all. And that is known. Okay. So if you look at solving, at trying to find feasible solutions for really large systems, you look at the bottom of the table. And what happens here is that even though the branch and bound didn't help, what you get at the root node is already a lot better than what you get just by the rounding approach that's well known. Different kind of constraints on the shunts, same set of problems, same approach. Here the rounding fails completely at the bottom, whereas the branch and bound achieves some improvements, as you can see in the light and in dark blues at the bottom. And then when we look at this adjustment of the generation to satisfy the frequency restriction, which is critical to keep the network functional, we basically, there's a little bit of a trick that you can use to simplify how you solve these things. But what I want to focus is the bottom here, the summary of results here at the bottom. We ran this for 15 instances, all with at least 1,000 buses. 5 scenarios per instance, so 75 cases in total. The rounding approach solved 31 cases to a very small gap. The branch and bound approach solved 46 cases to the same gap, so about 50% better in terms of the number of cases. But the most important part is the last line. The root, branch, and bound always found a solution. Not optimal necessarily, but it always found a feasible solution, whereas out of 75 cases, 30 times the rounding just couldn't find a solution at all. So you might do all the work and get nothing, whereas with the root, branch, and bound approach, at least in these cases, you always get a solution feasible for your problem. So in summary, the semi-definite approach is very effective at finding global optimal solutions for now realistic instances with several thousands of nodes. The computational times are still high, so there is still room to improve things. And in particular, as I was mentioning, the whole portal approach is something that still is very promising and needs to be looked at, and is something that I'm working on with some colleagues. In terms of challenges, well, there's a lot of things that can be done. The quarterly extensions already mentioned. I think we can do better also in using the general polynomial approach to this kind of problem. I think there's a lot to be done in mixed integer semi-definite optimization because we've only scratched the surface in this area. We have to think about uncertainty. I didn't talk about the fact that a lot of uncertainty is coming into the power system at the moment. And if you want more challenges, there's a lot of challenging aspects in this RPE competition because this is really aimed for real world problems. That's all that I have to speak about today. Thank you very much for your attention. You've got my website and my email, and I'm always happy to discuss and answer questions. Thank you.
Thank you so much, Miguel. Maybe we can start by taking a few questions from the virtual room. Please don't hesitate to ask your questions. The floor is yours now. Ne soyez pas timide.
You have one from the previous room.
Yeah, sure.
Thank you, Miguel, very much for this. Okay. Thank you again, Miguel, for this very nice big presentation. I'm not completely in the topic. I am curious about to see if you can comment what would happen in high dimension, for example, with respect to the big V matrix, which from what I understood, it in some sense translates the convexivization and the linearization objectives.
Yeah.
So
that is exactly what it does. I can just back up a few slides. Yeah, no, that's a very good point. I'm focusing here very much on the way it's done for ACOPF. But this technique in general, this technique in general works. So the first step in this technique is to say we have a quadratic problem, we linearize the quadratic terms, and we solve the semi-definite problem.
okay.
Now, let's suppose you still have the quadratic problem, but you haven't got the guarantee of global solution. You can build the next level matrix where you would take terms with degree up to 4. Okay, so you have a much bigger STP. You have a whole bunch of extra conditions. We have to define what this means. But essentially, you can keep increasing this approach and getting bigger and bigger semi-definite problems that in the limit will converge to the optimal solution, to the global optimal solution. This is what's called the Lasserre hierarchy.
Okay.
So this is a very special application of the Lasserre hierarchy at the low levels. But the general idea is if you're willing to make the semi-definite relaxations bigger and bigger and bigger, you do converge under some mild conditions. You will converge to the global optimal solution.
Okay. And at some time you also mentioned some kind of binary variable. Is that a way to remove some of the constraints when this variable takes 0, or this doesn't have nothing to do with that?
Not really.
Yeah.
You're removing terms. So what it's doing here is saying that for the power balance equation, let's look at the first one in this slide. This term that I talked about with the voltage squared is only there if the shunt at that bus is on.
Okay. Yeah.
Now, before I was ignoring that and basically assuming all the shunts are on, the terms are all there in the discussion. Now I'm being a bit more detailed and saying, actually, you can turn off the shunt.
Okay.
So I now have a variable that shows up and says, is this term there or not? But it's not an input, it's a decision of the optimization, whether to turn this on or not.
Okay.
Does that answer the question?
Yeah.
So that's really what it says. This is a bit different at the bottom. The tap changes are really, we're just setting different parameters as input. And we're turning inputs into variables within a range. And you know, it's a little bit different. But this is a very clean, at the top, it's a very clean binary idea. And by the way, you can now take this and apply the convexification of Lasserre and keep increasing the size of the problems, because this is just a polynomial and variables. Gets a bit more complicated because you're mixing binary and continuous and so on. But if nothing else, there is software that does it for you. You can just cross your fingers, plug it in, and see what happens. Okay. But you know, you always have to be aware that something can go wrong if you don't fit right into. But it's a very robust tool. I mean, this idea of bumping up the size of the semi-definite relaxations and getting better and better convexifications in general is a very good tool.
Okay, thank you very much for your detailed answer.
Any more questions from the virtual room? I think we got a problem. Actually, we cannot hear you.
I don't know if there's questions under the discussion.
Let me check. Actually, I have the discussion, but these are my messages for the
they're your messages.
Yeah. Okay. So if you can't hear us, I don't know, if we as we cannot hear you, don't hesitate to drop your question in the chat, please. Vous nous entendez?
Oui.
Je pense que ça va dans un seul.
J'ai l'impression que Rim parle là, non?
Ouais. Donc, mais on n'entend rien.
Non, on n'entend rien.
Ouais. Est-ce qu'il y a des questions? Do you have a question?
Yeah, ils nous entendent, mais nous, on ne les entend pas.
Ouais, c'est ça.
Yeah.
Ouais, on ne vous entend pas. Donc, essayez de mettre vos questions dans le chat en attendant, s'il vous plaît.
Voilà.
Non, on les entend pas, c'est vrai.
C'est écho.
Ok, donc la question c'est, y a-t-il une raison derrière, je vais peut-être activer mon micro, y a-t-il une raison derrière la restriction du calcul à 1 heure, 3600 secondes?
Pas particulièrement, non. Sauf peut-être la seule chose que je dirais, c'est que notre expérience, c'est que si c'est le point où ça en est après 3600 secondes, probablement ça ne changera pas beaucoup après. Mais c'est purement expérimental. C'est aussi le fait, je dirais, qu'en pratique, 1 heure, c'est déjà trop long. Si on veut résoudre ces problèmes-là, on veut le faire en dessous d'1 heure. Et donc, du point de vue pratique, 1 heure, c'est déjà amplement suffisant pour voir la capacité de la technique.
J'espère. Alors, il y a une autre question générale de Selma.
Oui.
De l'expérience de Miguel. Existe-t-il des méthodes d'optimisation appropriées par domaine, énergie, maintenance?
Des méthodes appropriées par domaine.
Oui, c'est-à-dire que est-ce que l'approche que tu utilises peut être adaptable à d'autres domaines qui sont
la réponse est sûrement oui. Donc, en fait, ce que je fais ici, c'est encore là, si on revient au tout début, c'est vraiment d'ici on parle. N'importe quelle formulation qui tombe dans, en fait, n'importe quelle formulation qui aurait, peut même être très large, optimiser un polynôme sujet à des contraintes de polynôme, on peut le faire. Même avec des variables binaires mêlées dans tout ça. Ça ne veut pas dire que ça va toujours fonctionner extrêmement bien. Et il y a des choses qu'il va falloir travailler. Mais en principe, oublions les binaires. Si on a un problème où on optimise un polynôme sujet à des contraintes de polynôme, moi, je n'ai rien à faire. Je prends le logiciel qui implémente la méthode de Lasserre et je l'applique. Ça, c'est étape 1. Si ça fonctionne, bravo, c'est fait. Sinon, là, il y a des choses à développer. Mais l'outillage en tant que tel est très général. Si on ajoute des binaires, là, il faut retravailler encore là un peu pour s'assurer, voir qu'est-ce qu'on peut faire. Mais certainement, je dirais, ce n'est pas du tout limité à la thématique de l'énergie ou à la thématique de l'OPF. c'est de l'outillage très général et je pense que c'est des idées très générales. D'ailleurs aussi, le résultat de Christian Bengané ici sur la convexification de ces ensembles-là, il y a toute une littérature, donc des ensembles comme S1, où il y a toute une littérature sur si on a des ensembles dans de petites dimensions qui ont une forme très non-friendly, comme on dirait en anglais, qui ne sont pas du tout gentils pour travailler, pour convexifier. Est-ce qu'on peut trouver des formules de convexification pour ces cas particuliers qui reviennent? Donc ici, c'est le ratio de deux variables et le ratio d'une variable avec le carré de l'autre. N'importe quoi qui rentre dans ce format-là, le résultat va s'appliquer. Parce que nous, on a convexifié ça indépendamment de l'application. Donc, le résultat ici n'a absolument rien à voir avec l'application. C'est motivé par l'application, point. Mais n'importe qui aurait besoin de convexifier quelque chose qui ressemble à S1 ici, de la forme de S1 ici, le résultat s'applique. Donc, en général, c'est des résultats quand même polyvalents dans ce sens-là. Très bien.
D'autres questions en ligne? En tout cas, n'hésitez pas à les mettre dans le chat. Moi, j'avais une question, peut-être vers la fin des slides, là où il y a les tableaux des simulations numériques.
Oui.
Il y avait quelque chose qui m'a un petit peu...
il y en avait trois.
Voilà, je pense le premier, c'est le premier tableau.
Le premier, c'est bon? Oui.
Du coup, là, la première résolution, c'est la value root.
Oui, donc la colonne ici.
Voilà, exactement. Et en termes de temps de convergence, parce que là, je vois que
on a le temps, donc le temps pour le root. C'est ça la question?
Versus.
Je ne l'ai pas ici. On l'a dans l'article, je l'ai enlevé pour ne pas pour réduire la quantité d'informations. Généralement, on peut le déduire un peu dans le sens que on est quand même capable, en une heure, d'aller chercher un certain nombre de nœuds ici. Donc, regardons les gros, disons. On est capable de résoudre, disons, 25 nœuds en une heure. Ça, c'est à peu près le même temps que le root. Donc, on parle d'à peu près 3600 secondes divisé par 25. Très, très approximatif. Ce serait le temps. Parce qu'une des choses, c'est peut-être la réponse plus générale, c'est qu'une des choses avec l'optimisation semi-définie, c'est que pour une taille donnée, généralement, le temps de résolution est toujours le même. Donc, c'est assez prédictible parce que c'est une méthode de point intérieur. Okay? Donc, si j'ai un problème de semi-défini, d'optimisation semi-définie d'une taille, mettons, 1000 par 1000, avec une certaine structure de contrainte, je peux rouler quelques cas et je peux m'attendre à toujours avoir à peu près le même temps. Donc, c'est vraiment le temps total divisé par le nombre de nœuds, c'est très proche de ce que ça coûte.
Et juste après, sur les slides d'après, je crois, il y a un choix de stratégie d'exploration de l'arborescence du branch and bound. Juste après.
Celui-là, oui.
Est-ce que c'est celui-là?
Oui. Celui-là en haut que j'ai passé rapidement? Ou...
Non, ce n'est pas celui-là. Là, oui. C'est peut-être le suivant alors.
Je pense que c'est le dernier, ça. C'est celui-ci?
Oui, exploration stratégie, c'est Depth First Search.
Oui.
Pour avoir déjà utilisé ça, à chaque fois qu'on change de stratégie, il y a un impact sur le temps de résolution. Quelle est l'explication que tu peux donner? Est-ce qu'il y a vraiment une stratégie d'exploration meilleure que d'autres ou ça dépend tout simplement de l'instance ou du problème?
Ça dépend beaucoup du problème et même de l'instance. Ici, dans ce cas-ci, tout est choisi pour essayer d'arriver à une solution admissible. Donc, depth first veut dire qu'on fixe des trucs, de plus en plus de choses pour essayer d'arriver à une solution admissible. C'est pour ça qu'on fait le branchement sur les variables qui sont le plus proches de 1. On pourrait le faire le plus proche de 0 aussi, mais là, on voit que par la structure du problème, si on branche à 1, le 1 va forcer d'autres variables à 0. Okay. Donc, tandis que si on branche à 0, ça a moins d'impact sur d'autres variables en termes d'effet domino. Donc, encore là, la motivation ici, c'est tout simplement, on veut essayer de tout fixer le plus vite possible pour arriver à une solution admissible. Même les trucs ici en bas d'arrondir les variables, maintenant, quand elles sont assez proches entre guillemets, parce que 0.25 et 0.75, certains diraient que ce n'est pas si proche que ça. Mais nous, on y était très agressifs. On s'est dit, ce qu'on veut, c'est trouver une solution, parce que juste trouver une solution, c'est déjà un défi dans ces problèmes-là. Donc, les choix ici, ce n'est pas pour dire que c'est des bons choix en général, c'est des choix très particuliers pour ce contexte-là, pour le besoin de la cause. Si le problème change, là, il faut revisiter ces décisions-là. Oui, très bien. Je vous remercie. Est-ce qu'il y a d'autres questions? Je ne vois pas dans le chat. Est-ce que je dois comprendre que peut-être vous n'avez pas de questions? Je regarde, j'ai une question de validation. Oui. Il y a quelque chose qui est dans le pipe, donc. Ça va. La question, je l'avais au fur et à mesure qu'elle arrive. Une question hybridation. Question online. Question online. Voilà, donc hier, on nous a présenté un cas RTE d'OPF pour la question à la Reactive. Donc, il y a eu une présentation hier, un séminaire chez nous sur des sujets visiblement qui sont un peu plus similaires. Mais c'est bien. Dans un cas où l'opérateur qui a mentionné tout à l'heure, en l'occurrence RTE, fait partie aussi de ce projet-là. Oui. Par contre, la question n'est toujours pas arrivée. Après, il y avait un petit sujet, c'était sur le rounding technique. Oui. J'imagine, il y a derrière un processus de vérification sur la faisabilité de la solution, parce que parfois, quand on arrondit à 1 ou on arrondit à 0, on n'a pas la garantie que forcément c'est quelque chose de réalisable, de faisable. Oui. Comment c'est fait dans le cas de... Ici, essentiellement, c'est fait dans le processus de branch and bound, vu qu'on fixe seulement... Bon, relativement, on ne fixe pas beaucoup de choses en même temps. On continue à brancher. Ce qui pourrait arriver, c'est qu'on arrive à un nœud qui n'a pas de solution. Donc, la relaxation n'a pas de solution. Et ça, on peut le détecter. Et si la relaxation semi-définie n'a pas de solution, ça veut dire qu'on a pris les mauvaises décisions. Et là, on peut faire un backtracking dans l'arbre de branchement et recommencer. On peut être plus intelligent que ça. Mais ici, ce n'était pas ça, c'était pas un des problèmes. OK, le reste de la question, du coup, peut-être on va s'arrêter là. Peut-on réutiliser des résultats d'optimisation pour brancher la méthode à des techniques de machine learning susceptibles de fonctionner? Je pense que c'est le mot hybridation. Est-ce qu'on peut coupler tout ça avec les aspects de machine learning? C'est le cœur de la question. De manière très générale, je pense que la réponse est oui, mais il s'agit de savoir qu'est-ce qu'on veut faire avec le couplage. Mais il n'y a aucune raison pour laquelle on ne puisse pas faire ça. Il pourrait y avoir, entre autres, si je pense juste en termes du branch and bound, il pourrait y avoir un couplage ici où ça pourrait peut-être guider la recherche. Donc, si on fait conjointement un aspect apprentissage, ça peut peut-être guider la recherche, parce qu'encore là, on revient à la question que, je reviens à la question que si je sais où aller regarder, c'est facile de trouver la solution. Donc, s'il y a une approche d'apprentissage qui me permet d'apprendre où aller regarder, ça rend mon problème beaucoup plus facile. La raison pour laquelle je dois faire un branch and bound, c'est que je dois chercher où aller explorer. Donc, pour moi, ce serait une possibilité d'hybridation assez directe dans ce sens-là. Mais il y en a sûrement d'autres. Très bien, merci. C'est bon pour nous, sans regret. Merci beaucoup. Merci Miguel encore une fois. Merci. Et merci à tous les participants en ligne et en présentiel. Ouais. Merci encore.